Good afternoon, everyone. Welcome back to the third session of the day. Yes, on industrial design technology, a new skill, a very, very futuristic skill, which is recently added to World Skills program, to the India Skills program. So, although last time it was placed as a future skill, this time it's going to be a real skill where our Indian competitors will be competing to win the gold, silver, and medal. Of course, will be competing for the medals. We have done concept art. We have done thinking process. We have done concept sketching. And now, today, we are going to learn the technological process for detailing in plastics by Mr. Sabyasachi Paldas. He's a professor of practice at Department of Design in IIT Delhi with a huge experience and lot of credits to his name. Let's invite Mr. Sabyasachi Paldas here for the workshop.
Hi
Welcome,
guys.
sir.
Hi. Hi everybody. I hope you can hear me loud and clear.
Yes, sir.
I would like to share my screen, so let's kind of talk about this.
Please.
All right, so let's look at industrial design, and let's look at the kind of process that you have. So you will be given a certain number of hours to actually run through an entire design exercise. So you start off from problem statement, then you have to understand or you have to define what the problem is. After that, you have to ideate, which means you have to make sketches. You have to analyze as to what your various ideas are. Out of all the ideas, you have to shortlist. Then after you've shortlisted your final idea, you have to make a final sketch. You have to model it in CAD. Then you have to render it. Post that, you have to do all the workings on it. So you'll have to select materials. You have to select the kind of process. So materials, I mean like whether it will be sheet metal, whether it will be plastic. In process, supposing you've selected plastics as the broad material, then you have to select what kind of plastic. According to that, you have to select the kind of process. Then you have to select, you have to detail it out, and then you have to look at how the entire thing comes together, how the assembly is. Post that, you also have to make drawings, and you have to finally make a full comprehensive presentation. Where's the challenge? The challenge is that you have just a couple of hours to actually do it, say about 15 hours or so to do the whole thing. That's where the challenge is. So, you might have come up with a certain very nice looking product, a concept. It can be anything. It can be like something like a drill. It can be something like processed food. I'm just showing you existing products, but of course, what you'll be developing is your own idea. Okay. The challenge is that you have to do all of this within the time period, and you have to detail it out probably within an hour or even less than that. Ideally, you should be able to detail it while you're ideating. So, moment you're kind of thinking about the form, the way it looks, the way it works, you're also mentally in parallel thinking about how the components are going to get made, what kind of materials, how will it be put together. All that should happen like muscle memory. So detailing also involves formal detailing, which means how the entire thing looks like, very fine little, like you see the little place for the thumb screw in the spoon. So something of that sort. Look at the way, say, pipes come and join together, how there's a nice intersection of forms that happen. or even how forms come together. So you have this very interesting hinge that happens with two arms, maybe of a table lamp or something, but it's a very nice looking form. So formal detailing is very important. So even something that kind of wraps around, cool looking things. You also have to look at product graphics. So how will it kind of, you have to give it a name. You have to see where that name comes. How will that name look like? So that also takes time, is what I'm saying. So given all of this, what we're going to talk about today, since we have limited time, I'm going to talk about detailing. You know, uh, and we're going to talk about detailing in specifically for injection molded plastic components. So you already, now I assume that you already have your form ready, your concept is ready, you have already modeled it out. You need to now detail it out, right? So I thought of, I'll kind of explain to you some of the concepts of the plastic injection molded detailing by looking at something which is pretty much everybody has seen, has used in their house. I'm looking at a plastic bucket. Okay, very simple plastic bucket. To simplify it, I have got rid of the handle, the hinge, and all that. So we're just looking at the body of the bucket, right? So it has got a lip and the rim on the top, and it has got a certain kind of feature at the base. It holds water. There is a certain pressure of water. You drag it from place to place. So it has to have a certain amount of rigidity and strength. So that kind of comes from your material selection. So what kind of material would you like to select? We are not getting into material selection today. We might do it at a certain later date, but I'm just kind of letting you know. So it's not enough that you just talk about plastic, but you also have to think about what grade of plastic. For example, buckets, etc. They are all made from commercial grade plastics, which are like high density polyethylene, HDPE, or polypropylene, like your tiffin box, all that. That is food grade. So that food grade means that it does not pass on the smell of the plastic to the food. It's not that it will contaminate the food. Plastics don't do that. But it's just that it does not impart its own smell to the food. That is food grade. So it's actually smell grade. And then you have engineering grade plastics. They're called engineering grade because the amount of shrinkage that happens is very, very controlled. Commercial grade plastics, the rate of shrinkage is not defined. It's not exactly the same every time. Okay. So when I'm talking about shrinkage, what is it that I need? Let's kind of talk about the process of it. So when I'm kind of talking about injection molding, it's a machine that has got a mold in it. The mold shuts and opens up. What you put into the mold, into the machine, is what you see on the top right hand side. This is called resin. So it's like pellets. It's like grains of sugar. And for different colors, you have different master batches. And you put in, say, you want yellow ones, you put in yellow resin. You want a blue component, you put in a blue resin. And what happens is, if you look at, there's a nozzle. So it kind of heats up into the barrel. It melts. It becomes like very hot honey. So extremely hot and extremely viscous. And the whole thing is pushed in like an injection syringe into a cavity, which is called a mold, and it kind of moves into the mold, fills it up, and then it cools down. So when it cools down, it shrinks. For a commercial grade, the shrinkage is not exactly controlled. And here I'm talking of shrinkage in the range of about 0.01% or 0.1%, or maybe at the most 1%. So that is the kind of high degree of tolerance that plastics have. right? And then the mold opens and the component can be taken out, right? So that is something that you need to kind of read about a bit more, understand, and then we have to design keeping in mind the constraints of the process. That is what is important. And that is what we'll try and understand what are those constraints of the process, right? So let's get back to our bucket. As a product designer, you must always kind of start thinking about how to section things and how to look at how your wall thickness is. So after you have your product ready, the first thing that you should think about is wall thickness. How much of wall thickness should be adequate for a product that I have designed? I can give you some examples. Like for example, look at this bucket. It has got a wall thickness of about 1.5 to about 1.8 maximum here, not more than that. So you don't really require a lot of thickness. If you require strength, what you actually do is you have to do lipping. So I'm going to come to that. So what is very important for product detailing is that your general wall thickness must be uniform. So if you've taken 1.5 mm, no matter what kind of twists or turns that you have going right across, the thickness should be the same as much as you can manage. Okay, so that is something that is the first thing that you can choose. Of course, depending on the kind of usage, depending on the kind of material choice, the thicknesses will change. Say, for example, you have, like a medical product, or you have something like a mixie or something. So there, your wall thickness might be about 2 mm, 2.2 mm. You have a drill bit or a machine drill, a motorized drill. So there, you might use a reinforced plastic because it's taking a lot of stress and strain on the component, and it might have nylon filling. It might have glass filling and in nylon. There the wall thickness can go up, say about 2.2 to 2.5. So this is something that, with experience, you have to study and experience that you have to do. You have to kind of pick up that if this is my application, this will be my wall thickness range that I'm kind of doing, right? Let's talk about stiffening a component. So if you look at your bucket, which you're fairly familiar with, if you notice on the top, you have a rim. And it is not, just ending in the wall thickness. It's kind of turned up once and then twice. What that lipping does is that the lipping strengthens the component. Have you ever tried cutting the top portion off? Then your bucket will not retain its geometry. So the lips are very important to retain geometry, not adding thickness. That's very important to understand, right? Look at all the corners. So corners in plastics should never ever be sharp, whether internal or external. So even if you have an internal corner, you must give it a minimum radius, say about 0.5 mm or so. That is an absolute must. And ideally, the radii should be concentric. Yeah. So you have your internal radius, you add the thickness, and that becomes your external radius. So that is very important. The second thing that you notice in a bucket, if I may just go back, see the sides are never straight, they're not parallel to each other. So it's actually a frustum. A bucket is a frustum. And it's a frustum because you need to take it out of the mold. So imagine if it was a pure cylinder in shape, the resin will cool down, it will shrink, and it will really hold on to the core of the mold, and you will not be able to strip it out. So it's very important that you need to give it a draft angle. So draft angle is something that allows the component to come out of the mold You have a draft angle from half a degree to about 2 degrees. In engineering grade, in commercial grade, like in a bucket or so, you have a draft angle of about 5 degrees. Yeah. So unless until you give higher drafts, it will not come out for commercial grade plastics. So that is important to remember and understand. Right. So look at this. Look at how the internal, the external, they are all exactly following the same thickness. The radii are concentric. There is a draft. Even for the lipping on the outside, there is a draft. So any injection molded plastic component has to have draft. Okay. Let's look at the base. So, I'm looking at the top and look at the base. Notice a couple of things. Notice that there is actually a rib. There is a rib running around the periphery, close to the circumference. All right. Why do we have a rib? We have a rib because so that when you drag, maybe you fill the bucket up and you want to kind of shift it. So most people will not lift it and put it down. They will push it. So what happens is that the entire surface actually is rubbed against the floor. Imagine if there was no rib like this, which is running around, then your entire bottom will start getting scraped. Yeah, that's not such a good idea. You look at any small product, like you look at your remote or something, you'll find there are small little tips on the rear surface. Or you look at your mouse, there are little feet there. So the mouse feet is to help you move your mouse more easily. If you have a remote or something, they've got these little projections or little tips coming out like hemispheres. And those are actually to keep the entire surface away from wherever you're keeping it on from. So if you even move it around, or what happens is it's those little small points that are actually touching the surface and not the entire surface. So your entire surface will not scratch. That is important. Also, it's important to look at a certain amount of engineering aspects whenever you are teaching. There are buckets, the good ones, have got a dome at the bottom, if you notice, or there is some sort of a smaller frustum at the base. It's never generally flat. If it's flat, then it's got more rings. Maybe there's another ring in the middle somewhere and all that. Why is this? It's there because there is entire weight of the water that is actually say about 15 liters or so. So that's 15 kgs of water weight is actually coming on the bottom. And if it's not pre-cambered, which means it's not domed, it will sag. Try and see wherever you're seeing something of this sort. I'll give you an example. Look at a bridge. Look at the deck of the bridge. You find the deck of the bridge flat? No. See, a deck of the bridge always has a pre-camber. So it's always kind of raised up in the middle and going down to the sides. When you're crossing a bridge, you also have to climb up and then you kind of go down. Right. So the same kind of engineering principles are applied even to a bucket. So it's very important to make these, interesting connections and be aware of these things. That's very important for industry. So yeah, so you have this, very interesting pre-camber, and that actually adds to the strength of the component. So you use geometry, not wall thickness, to add to strength. See, these are all things that are part of detailing. And as you keep working on more and more products, these are the kind of things that should come automatically. Remember, I was talking about muscle memory. So there are certain things that you need to resolve at the same time. I'm showing you two more things right here. Look at, there's a little hump in the middle. Why? Notice all your buckets. It will have, feel the bottom. It will have this little hump. That's because on the other side is actually the injection point. And there is a certain amount of thickening there so that when this liquid resin kind of gets injected at very high uh, velocity and very high pressure, it doesn't kind of, push back. So there is enough space for the liquid to come out into the mold and actually spread all over. The amount of pressure that you put in to actually form a bucket, the plastic injection force is very high. So it's about almost, you put it on something like a 60 or an 80-ton machine. So if you take African elephant full grown, that's about 4 tons. So you have 20 African elephants. The amount of pressure that is actually being put on to actually inject that resin into this mold. That's the kind of pressures we're talking about. Okay, so imagine that. Also, look at, there are certain cuts in the rim at the bottom. Can you see that? Good buckets will have this little cuts at the base. Imagine your floor is wet, there is water, and you then put your bucket down. The rest of the water kind of flows out, but supposing these cuts are not there, then the water inside is going to get trapped. When you want to lift the bucket up, you will almost not be able to do that because it kind of acts like a suction pump. So it completely sticks onto the surface because there is no cuts in the base to allow the water to come out. Or imagine there's water all around and there's air inside. So that is something that to prevent that. So these are the kind of things you have to kind of put into your product detailing when you are working on this, right? I'm just kind of making you aware of these very small things. It might sound a little daunting right now, but this comes with practice and with sharp observation. See, that's the way the base is. Okay, so look at the rib. See, everything that you have has to have a certain formula with it. So let's look at a rib. So you have a rib which has got a draft angle. It has to have a draft on both sides because imagine your mold opening is perpendicular. So you need to have a draft on both sides. Your wall thickness is T, if I take it as T. So your base of the rib should be between 0.4 to 0.6 of your general wall thickness. That's very important. You must always have everything filleted. That's important. Your rib height or the rib depth should not exceed 5 times the base thickness. There's something in architecture called slenderness ratio. So it's a bit equivalent to that. So these are kind of things that you need to read about and automatically incorporate in your detail. Yeah. For want of time, I'm kind of moving on. So imagine we are not looking at something which is as simple as a bucket, but imagine you have designed a product which has got electronics inside. It's got a lot of things happening. There's got motors and there's got PCB and there's USB connectors. All that is kind of happening. And what you actually have is you have two components. You have the top and the base. Notice the way the top and the base are actually joined together. This is a very classic clamshell design. So it's very important for you to kind of take components apart or take products apart that are not working and actually notice how the joining details have been worked out. Also notice that there are snaps, like there's a yellow snap that you can kind of see. And that goes on and snaps on to the top plate. So plastics, even though the name is plastic, is also to a certain degree elastic. So they can kind of bend and come back to its original position within a certain limit. But if it goes beyond that limit, of course, it will break. It is plastic after all. It is not rubberized. It is not elastic. So we have to kind of understand and detail in as to how much can it move and how much can't. So let's kind of look at a few more details. So this is a very typical clamshell design. Yeah. So you have a top and the bottom, and you have a lot of things happening. You might have something like covers for battery, for the other things that you can access. So that's how typically a construction of a clamshell design is. Now also look out for things like ribs that are inside, which are kind of holding on to the bezel. Yeah. So that lip detail that we talked about actually sits all around the bezel. Let's look at a snap. So how do you design a snap? So it has got a certain formula there. So you know how much of the snap land area that you have to kind of give, uh, and vis-a-vis the amount of height, the wall thickness that you have, right? So the way that ribs are, that ideally they should be tapered. So there is a way in which it comes out on this side as your mold opens. On this side, on the side on which the snap is, there has to be something like a pull out. So within the mold, there has to be a pull that will move out of the way before the component can get released. You just need to know this much. You need not get into too much of detail, but it's important that you need to know that there are things called pullouts that kind of move inside the mold for the component to get released. Moment you have details of this sort, right? So there is a certain length, there is a certain thickness that you already have. You have a base thickness, which is about half of your general wall thickness. There's a certain taper that happens, and once you apply this formula, you get a fair idea about what your snap dimensions do. Okay. I'm also going to try and see whether you can kind of access these things later on. So this is just to kind of familiarize you with what are the kind of details that are important and to be studied. You can also go on the net and actually type in these kind of details, how to detail out a snap, and there are enough material on the net that you can actually access. But what is important is that you have to keep doing this again and again, so that when you are actually part of the competition, then you can't refer back to these things. These things have to be part of your muscle memory. So if you have a snap, it should take you like, within a second, you should be able to kind of design the snap and build it into your model. This only comes through practice. Of course, first you have to be very, very aware as to what the components of a plastic component, what are the various details of a plastic component could be, and then design accordingly. So you can also kind of design snaps that do not require pullouts. So I'll just kind of try and explain this to you. So if you look at this battery cover, which goes and snaps in. So if you look at the blue arrows, that's the direction in which the mold is parting. Okay. And the way the snap is designed, you need not have a side pull or something that is kind of getting pulled out. So also the direction of mold movement, the way your components are getting assembled, that is very important to be able, you have to be very aware of when you're designing your snaps. Another thing that is a very recurring detail in injection molded plastic components is something called a boss. Okay, it is essentially like a frustum, and you have various things that essentially are mounted onto it. Your PCB might have a hole which might go into the boss, so it will not allow, you know, it will restrict the degrees of freedom of motion, and it will not allow the things to move around. You can anchor things to a boss. You can have a peg that goes into a boss. So these are the kind of things that basically allow for placement. So again, draft angle, extremely important. Everything has to have fillets. Plastics should not have any sharp corners, because sharp corners means then that you are having stress concentrations. Plastics are very, very susceptible to stress concentration, unlike sheet metal. Okay. Or you have cast components in any kind of alloy, in aluminum alloy. They might have, ideally not, but plastics should never have. The second thing that is important to know is that the way the well of the boss, if I may call it, is kind of going down and interfering into the wall thickness. So if your wall thickness, general wall thickness is T, say 2 mm or something, the amount of gap that you see there is about 0.6. Okay, so it's about like 1.2. If that's it. Now, why is that? That's because what's happening is that when if you don't give that, you get something called a sink mark. So from outside, you will get a slight depression on the surface. That looks like a very bad, surface detail. So to avoid all that, you need to kind of reduce the wall thickness there. So the amount of material shrinkage that's going to happen, it's going to be less because there's less material. So the amount of sink that's going to happen is going to happen less. Very, very simple points, but these are things that will actually help you design and detail the product to a much higher degree of finesse. See, this is not just, detailing, but it is also showing off your engineering skills. It is showing off your design sensitivity. It is showing off your process skills. So these are the kind of things that are important to demonstrate. Looks like a lot, but actually, as you keep using them, it will become part and parcel, like breathing. So what happens when you have ribs and bosses coming together? Okay, so you can kind of have a boss and then have a rib, because what happens is when you put a rib around the boss, with 2 of them, 4 of them, then you're really strengthening it. So the entire mantra in plastics is, if you need strength, rib it, lip it, add a surface indentation, change the profile, but never add to things. That is a very wrong process, a very wrong approach, right? So in order to kind of buttress your rib, in order to strengthen your boss, rib it. So if you have, you need a surface, or look at your printer or something, look at the kind of base of the paper tray and all that. It's highly ribbed at the base. The top might be flat, but they're very fine ribs, maybe running right across, both in the X and Y directions, that really make the component very, very stiff. So that's the way to stiffen a component in plastics. This is something that will require a little bit of understanding. This, supposing you have 2 components coming together, or you have a PCB that you want to fasten to a plastic component. So what you have actually is, you have a boss, you have a fastener, which is a self-tapping screw, and which basically cuts a thread into the boss and holds on. Couple of things to be noted. If you have, say, 2 components, like you're showing in the diagram here, say you have a top component and you have a bottom component with the boss built in. It's a very good practice to add another boss around it. See here, you have to look at 6 degrees of freedom of motion. So you have x plus x minus, y plus y minus, z plus z minus. Look at what happens when you add that little boss around in the top quadrant. So if I take horizontally x plus x minus, that completely gets taken care of by the two bosses coming and meeting with each other. Y plus y minus, which is going into the screen and away from your screen, that is also taken care of. Along the center line, which is the red line, imagine that's the z-axis. So it can't go down because, so your z minus doesn't work because you have your material, falling one over the other. So it can't obviously go down. The only direction it can move is z plus. So it can only go up. And that is being prevented from moving up by this self-tapping screw. Screws should never be in shear. That holds for sheet metal detailing, that holds for plastic detailing. So if you had not given this little boss on the top, I'm talking about this thing, this little boss here, the screw would be in shear. So there would be nothing preventing it from this component and this component to slide against one another except this screw. Just because you've added this boss is what is preventing at least 4 degrees of freedom of motion from not happening. It does not allow it. That's a very good detail. It doesn't cost anything because it's already built and part of the component, but it really increases the life of the component. Okay. Let me spend a little more time on this. Okay. So what you can notice here is that, of course, the draft angles are here, but there is a certain amount of larger opening here. And this is actually the diameter into which your screw will actually start engaging with. So if you notice, if your screw has a diameter of small d, this has to have about 0.8. So it will start engaging with these threads. And of course, you have your draft angle here. So as you keep tightening the screw, it will dig in deeper and deeper. What happens is when you keep rotating the screw, the material that is cut out actually starts traveling back and starts accumulating here. It kind of comes up. If you notice, like, you have a backhoe and you have a large screw for a pile driving or something, look at a, construction site. So when the pile goes into the earth actually starts coming out. You see, you can't destroy, you can't create or destroy material. So material has to move away. If you're taking it out, it has to move somewhere. You're digging a hole. So your earth has to come out. Same way you're scraping the sides of this boss. So the scraped material has to come out. If you don't give this kind of a little, wider space here, what happens is the material that is kind of scraped up starts actually pushing against the component on the top. This little space here actually allows for the cut material to kind of rest there. And it never kind of pushes the material up and the component up. So it will perfectly sit when you are kind of, cutting the screw in and allowing it to rest. And there'll be no upward thrust. These are very small things, but these are very critical to understand and build. It doesn't take time once you've understood the concept and once you've kind of practiced doing this detail over and over and over again. That's very important. We would like all of you to kind of get into this level of detail and kind of wow your jury members with your understanding of not only the entire problem area, not only about very nice form, about not only good usability, ergonomics, but also your good amount of demonstration of manufacturability. So these are all manufacturable details, and that is what we are actually aiming towards, right? This kind of more or less kind of brings me to the end. Thank you so much. I would like to kind of ask you guys to come back with your thoughts.
Thank you. So sorry, I was talking on mute.
Sorry.
So thank you for the wonderful workshop. It was very, very detailed details that you have given about the plastic industrial designing, these techniques and the process. So
Right.
I got one question, and I think that's very important. Is it different from metal? Like there is a different process for metal and different process for plastic?
Oh yes, of course. So I mean the basic, if you're looking at casting and all that, essentially what we're looking at like draft angles, etc., are more or less the same. But I mean, if you're looking at pressure die casting, pretty much similar. But if you're looking at sand casting, then of course the uh, concepts are the same, but the details vary. So the amount of work that you have to give, all that is actually changed completely. Sheet metal is something that is again a completely different line of thought. So I think somebody or the other will have to kind of talk about sheet metal detailing. So I mean, so they get a good idea about how plastics are detailed, how sheet metal is detailed, what are the kind of processes that are there. So laser cutting, press brake, bending, and what all can you do, and what are the kind of constraints, limitations, and what are the other things that are possible.
Okay, great. So we'll plan another session for the metals, sheet metal especially. And yes, thank you so much, sir, for this detailed presentation and detailed workshop for the
Okay,
candidate.
I have two questions. One is I would like to kind of maybe make this into a document and kind of send it across to you, so all the participants can kind of refer back.
Yeah, sure.
So this is
That would
something
be
that they can refer back. So they should not get kind of frazzled or tense that they have not been able to write things down. Or they're not able to. The idea is not to kind of this is not a class that you have to write things down. This is to understand and get a first-hand quick idea, and then these things will probably be shared with you so that you can kind of look at it. This is just like talking about the top of the iceberg. So you
sure, sir.
really need to go down and understand yourself. How well you do that will also determine the quality of work that you can produce.
Certainly, sir. Once
The
we have
second thing is if they have any questions immediately, uh,
I'll
on the
quickly check
chat or
for the.
something.
Let me check. So the one important one that I've received was about the sheet metal. If it's different from if it's
Completely different.
different
Yeah.
process. And the third is how do you maintain the consistency of your product?
Can that be a little more? The question is not very clear. What do you mean by consistency?
Quality-wise, consistent product.
Sorry.
I didn't understand.
Okay. So maybe the person can on chat, if you can just write down what is it that you are talking about. Maybe I could answer it right here.
Sure.
I've got about 3 minutes left. So
yeah. So if you'll quickly write, I'll read it for you.
Yeah.
Okay. So what they're saying is if there are different parts that attach, how to maintain their quality, that they remain equal. How to ensure the quality remains equal for all the products.
By equal, you mean, are you talking about the quality of the fit? I mean,
yes.
How do they come and assemble together?
Yes.
Okay, so if that is your question, if I have kind of understood, you might have a different question, but I'm just kind of answering what I have understood. That first your fit and the way your components kind of come together and assemble, that starts off from how you are modeling your part. So if you have a certain, compound surface, and then you have two components coming and joining together over the compound surface, so that will happen as to right at your modeling stage. So I would recommend that, say you're doing surface modeling or you're doing solids modeling, whatever it is, and then you create a surface and then you actually part them or then you slice them and then you put in all your details so that at least your outer surface, your matching of the surfaces, that kind of remains perfect right from the beginning. So that's from a, I would say, a modeling point of view. And then if you have dissimilar materials coming in, so you have kind of sheet metal coming in with plastic, or you have two kinds of plastics coming in. So let's start with two different kind of plastics. So ideally, never mix and match. Like never put an engineering grade plastic with a commercial grade. Please don't do that. Keep both engineering grade plastics. For example, one is an ABS, acrylonitrile butadiene styrene. That's a kind of plastic. Please read about all this. I mean, and then the other component might be a polycarbonate component because you need visibility or clarity, or you want to kind of, there's a light or something coming out from inside to outside. So those are both are engineering grade plastics, similar degree of shrinkage. So you can kind of join them together. Moment you have dissimilar materials, okay, look at the coefficient of linear expansion. So look at sheet metal. Imagine you are putting it in sunlight. It's kind of warming up. Yeah. So sheet metal obviously will expand much more than plastic. So give greater tolerances. So if you have fastening there, have larger holes, slots, so things can move, and then still, even if you have a low degree of tolerance, they still kind of join together. Yeah, my time is up.
Thank you so much for answering the question, sir. It's a pleasure having you here and pleasure having you with us as an expert.
Thank you.
Thank you so much for your time. And thank you so much, everybody. I'm sure I will be sending you these documents in email shortly as we receive from sir. We are going to share it with all the registered candidates of industrial design technology for your so you may review and work on it. Thank you so much.
Thank you so much.
Have a good evening, sir.
Thanks. Bye.
Okay. Bye, everybody. We'll see you for print media technology at 2 o'clock. Bye-bye.